In this video, we're going to talk about direct proof with cases. And so, what is a direct proof with cases? Well, let's just move on to an example so you can see this idea in action. So here's our first example we're going to do, and it says if x and y is odd, then what? Then x is odd and y is odd. So the idea, just like we did last time, what we want to do is we want to start with the words proof. So we'll write PF. This stands for proof, and we will assume our P. So here's our P, and here's our Q over here. So we want to assume P. So let's suppose x times y is odd. And I guess we're also assuming x and y are integers, but let's suppose that's given. So let's just suppose x and y is odd. And then we have cases that we can run through and check. Because we know that either x is even or x is odd, and y is even or y is odd. So let's look at case 1. Or I guess we should say then, so then, oh, I don't need that. No. Let's just look at the cases. So case 1. So case 1 would be, we can just make this up basically, right? So it's like, oh, let's let x be even and y be even. And I guess we should say, assume here. So let's do that. So we should say something like, suppose. You have an eraser, so you can just erase it. So suppose x is even and y is even. Then what? Right, so then we know that x is equal to, let's say, 2a, and b is equal to, well, not b, but y. I'm thinking ahead of myself. And y is equal to 2b, where a and b are certainly integers, so element of z. And this is by definition of even. Okay, and then we want to do what? Well, you want to notice that if you multiply these things, so notice x times y would be equal to 2a times 2b, which equals 4 times ab, or you can say this equals 2 times 2ab, which is even. Right, but we know that what do we know? We know that xy is odd. This means what? This means not both x and y are even. All right, so there's case 1. We know now that both x and y are not even, so let's do another case. We'll call it, of course, case 2. And so here now we'll suppose what? Suppose x is even. Suppose x even. And how about y? Y is not even, but y will be odd. Then we do the whole thing sort of again. So then we know x is equal to 2a, and y is equal to 2b plus 1, where a and b are integers by definition. And let's just put by definition, because it's clear by definition of even and odd. All right, now what? Okay, so then you want to notice, right, notice what? If we take x times y, what do we get? We get 2a times 2b plus 1, which is equal to, let's just point this out, 2 times a, and we'll put this in square brackets so that makes it real clear, 2b plus 1. All right, which is not odd, but even, which is even. Thus what? Thus, x cannot be even when y is odd for the same reason as before. For the same reason, as before in case 1. Just so if it's not clear what I mean by same reason as before, the same reason before was that we had this xy being odd and xy being even. Now we have xy being even, so now we know, again, x can't be even when y is odd for the same reason as before, which is the reason above in case 1. Okay, let's try another case. So case 3, suppose now x is odd, so x odd, and y even. But this can't be the case because this is basically case 2. Right? There's really no difference between x and y in some sense. So we can say, but this cannot happen by case 2. And then finally, our final case, case 4, when they're both odd. So suppose x is odd and y is odd. Right, then, so same sort of setup. We know x is equal to 2a plus 1, and b is equal to oops, again, I got ahead of myself, right? So, and y is equal to 2b plus 1, where what? Where a and b are integers, and this is by definition. If you want to write by the definition of even and odd, you can, but I think it's pretty clear it's by definition implies the definition of, which is just odd, right? By definition of odd. And then what would you want to do? You want to notice, so notice what? Notice x times y is equal to what? Is equal to 2a plus 1 times 2b plus 1, which is equal to what? Well, if you multiply this out, you're going to get a 4ab plus a 2a plus a 2b plus a 1, which equals, we can factor out a 2 out of the beginning, and get 2ab plus a plus b in parentheses, and then plus 1. And this is clearly, which is not even, but odd. So therefore, x and y are both odd. And we did this by cases. So, here the idea is we assume P, and then we just go through case by case. So there are 4 cases basically. X and y can both be even, and we see that can't be the case. X is even and y is odd, and we see again that can't be the case because you get an even number out, of course. And then suppose x odd and y even, and now that can't be the case. This is really sort of by symmetry in some sense because there's no real difference between x and y. So case 2 and case 3 are basically the same, or the arguments are basically the same. And then finally, case 4, we see that, yeah, if x is odd and y is odd, that it is true. That is, this is going to be odd. So x and y are both odd. I actually proved something a little bit stronger here, but I don't want to point that out right now. But I want to make a point of it's just the idea of using cases to prove something. Let's go on to the next thing, which was, what does WLOG mean? And so WLOG, what it means is without loss of generality. And that's what WLOG stands for. We use this a lot in proofs, and the idea is that we use without loss of generality when, in some sense, if you're using 2 letters like x and y, and we want to prove something about x and y, but it really doesn't matter if x has that property or y has that property. So let me give you an example real quick. I think that's the best way to kind of see this. So here's the example we're going to do. So the proposition is if 2 integers have opposite parity, so that means like one is odd and one is even, then their sum is odd. So this is our P right here, and then this is our Q, of course. And we want to prove this. All right, so here's our P and here's our Q. And so to prove this, if you look at a proof of this, you may see something that says WLOG, which, remember, means without loss of generality. Oops. Generality there. So without loss of generality, assume, and that's terrible, assume. Here, let's try this again. So without loss of generality, assume x is even and y is odd. Right, so the idea is you don't have to do 2 cases here. We can just say without loss of generality, we'll assume x is even and y is odd. And the idea is you don't lose generality because you could then just assume y is even and x is odd and follow exactly the same argument and arrive at the same conclusion. So then we have x is equal to, of course, 2a, and we'll have y equal to 2b plus 1 because it's odd, and then where a and b are integers, and this follows by definition. And then we want to notice, well, notice what? Let's notice, and let's go down here, x times y, or their sum, sorry, not their product, but their sum, x plus y, which is equal to, what's it equal to? Well, x is 2a, so we write down 2a, plus, and of course y is 2b plus 1, 2b plus 1. And we want to show that this thing is odd, and so I'm looking for like 2 times a number plus 1, and you see that right there. Just pull out the 2. So 2 times a plus b plus 1, which is equal to, let's make this real clear, right? So 2 times c plus 1, where c equal to a plus b is an integer, so element of z. Right, so, and then we can say hence x times y equal to 2c plus 1 is odd. By definition, and you say by the definition of odd, or you can just say by definition. I really think it's clear what we're referring to here. So by definition. And then let's end with our therefore. So therefore what? Therefore their sum is odd. All done. And so that's what we mean by without loss of generality. And again, you could prove this without using that statement. So the next case would be assume now x is odd and y is even, and you'd follow exactly the same argument and arrive at exactly the same conclusion. But without loss of generality kind of saves you that step. Going back up to the last proof, in some sense, you could do case 2 and case 3 together and say, case 2, case 3 combined, say without loss of generality, we'll assume x is even and y is odd. And then that would do both these cases because the arguments would be exactly the same. Instead of just saying, but this cannot happen by case 2 because basically they're the same case. And I think that completes this video.